West Churchman, a critically minded systems thinker, struggled with the limitations of rationalistic understanding presented by a dominant rationalistic systems paradigm. Churchman grew disillusioned with the narrow analytic understanding that dominated the operations research community that he himself had helped shape. He and his colleague Russell Ackoff ultimately abandoned these fields, since in Ackoff's words, their systems approach had degenerated into mathematical masturbation. It was disinterested in its real-world context and unable to recognize its own shortcomings. Churchman, throughout his work, strived to reconcile the comprehensive aim of a systems approach with the recognition that the reductive approach, represented by these specific forms of systems analysis, seemed to violate the very principles of systems thinking. Now, systems thinking is a very broad term used to reference an enormous variety of work that is typically classified in a range of disciplines. Now, I can't provide a comprehensive historical overview, but I want to retrace a few core concepts and developments. Because of the diversity inherent in systems thinking, it can be difficult to understand what makes an approach systemic. And systems thinking is often antidisciplinary, or at least it sits uneasy with the disciplinary categories. In contrast to the vertical deep dive on investigation based on disciplinary theories, systems thinking approaches tend to transcend or disregard disciplinary perspectives. The main reason is that disciplinary boundaries are rarely aligned with the phenomena of interest. Systems thinking, therefore, often favors a grounding in the empirical complexity and structure of the world. The central concept shared across systems thinking is the realization that there are aspects of interest of the world that cannot easily be decomposed into constituent segments without disappearing or losing their meaning. The central idea of systems thinking is that to make sense of the complexity of the world, we need to look at it in terms of wholes and relationships, rather than splitting it down into its parts and looking at each in isolation. This idea arose in many different fields, from biology to family therapy, from psychology to climate science, from ecology to pedagogy, from economics to organizational theory. In a reader edited by Ramage and Shipp, from which this diagram is taken, 30 selected systems thinkers are grouped into 7 categories: early cybernetics, general systems theory, system dynamics, complexity theory, learning systems, later cybernetics, and soft and critical systems thinking. These various approaches to systems thinking have little in common in terms of their content. What they have in common is a way of thinking that places primary attention to thinking about wholes and how they are constituted and organized in given contexts. The few concepts that play central roles in some form to most systems thinkers are emergent properties, structure and organization, boundary and environment, and communication and control. But those 4 key concepts are defined and enacted across different systems approaches in wildly divergent ways, contingent not only on the domain in which each systems thinker operates, but also their epistemological commitments. Few disciplines have not seen some form of systems thinking, whether it's anthropology, psychology, education, biology, climate science, management, or computing. The proliferation of the systems term in our colloquial language, the healthcare system, the education system, the transportation system, the information system, it also indicates that many fields are inherently looking at systems of education, management, public health, and so on. The century-long history of systems thinking has also resulted in systemic thought dissipating deep into the way we reason commonly about the world. But ultimately, systems thinking as an approach is fundamentally opposed to disciplinary views, because disciplinary science is essentially isolated by its disciplinary politics and therefore unable to engage with the full meaning of the world. Or as Churchman wrote, disciplinary science must not be trusted by the science of the systems approach. Disciplinary science's insistence on a very narrow meaning of control in experimentation, for example, must be regarded by the systems approach with a great deal of suspicion. In fact, disciplinary science may very well be a political device to convert broad-minded PhD students who want to study big problems into narrow-minded assistant professors who study small problems in accordance with accepted standards of research. Because systems thinking approaches have been built across such diverse fields out of heterogeneous ontological and epistemological commitments, they ultimately have very little in common other than this commitment to struggle with the aim for a holistic understanding of the issues they face. Whatever the scale that a systems approach emerges in, whether it's a biological unit like a cell, as in general systems theory, or a social unit such as a family, or a cognitive unit in psychology, or a learning unit such as in pedagogy and so on, the system concept embodies the idea of a set of elements connected together which form a whole, this whole showing properties which are properties of the whole rather than properties of its component parts. These properties are called emergent properties. The concept of emergence is one of the few that is relevant to all systems approaches, but they diverge wildly on how they conceptualize it and how they approach the question how the elements they are interested in are organized and what kind of elements there are. Some system approaches provide specific structural models of the systems they're interested in. For example, system dynamics, shown on the lower left, represents structural relationships between quantifiable variables as causal loops that can be expressed as equations. Soft systems methodology uses purposeful activity models, such as the one showing on the lower right, to reason through the contingency of goal-directed activities that are relevant to a social situation. Where system dynamics considers measurable variables that represent structural properties of the world, such as the number of people currently alive or the amount of carbon dioxide emitted yearly, and organizes these variables with quantitative causal relationships that allow it to predict overall behavior as the emergent property. Soft systems thinking considers purposeful human activities as its element, and the contingency of each activity on other activities is its main organizational relationship in the purposeful activity models in soft systems methodology. Other systems thinking approaches, such as the critical systems heuristics we'll meet later, do none of that sort. Even within this sample of models, not all assume that their models are in fact models of reality. Many approaches do assume that their models and representations reflect elements or structural properties of the real world. For others, like for Checkland, systems concepts are ideas, mental or discursive constructs that are used to make sense of the world, whether that world is systemic or not. The purpose of activity models in SSM is not to model real activities, but to develop a structure for a conversation about a social situation. And in fact, Checkland rejects the idea that the social world itself can be meaningfully represented in models. Instead, models are used to organize the conversation about a real world that is assumed to be essentially chaotic. And yet other approaches are agnostic to that distinction, and instead they focus on how either type of claim is discursively established. Equally, while some system approaches take the system boundary as a given and natural thing, critical systems heuristics, for example, focuses all its attention on boundary judgments as the central discursive act of planning and of design. So these three kinds of assumptions in particular are commonly used to distinguish between hard, soft, and critical systems thinking. Besides emergence in questions of organization, a central concept that unites and simultaneously distinguishes all three groups of systems thinking approaches is the issue of a given system's environment and whether it's treated as an unproblematic given, a central design choice, or a never-ending question. When we speak about sustainability, we meet primarily two types of systems approaches. The first is system dynamics, the approach that underpinned the influential report on the limits to growth and is central to various efforts to understanding, modeling, and predicting the human influence on the climate. System dynamics provides a conceptual framework within which we can distinguish direct, indirect, and large-scale structural effects of systems design choices, and that helps us to explore nonlinear, counterintuitive effects. Its epistemology is structuralist. The assumption is that by modeling structural properties of the world, its future evolution can be predicted given a set of assumptions. Because of its hard orientation, system dynamics has little to say about where its structures come from, where its assumptions come from, how to justify itself, and who gets to decide. Its direction is analytic. It proceeds by decomposing the whole system into constituent variables until they are considered sufficient to explain the observable behavior of interest, often without being reflective or critical about the boundaries of the system of interest. After all, It has to assume some boundaries, or else it could not deploy its formidable analytic framework. In its ontological assumptions, system dynamics continues the systems thinking approaches that churchmen opposed in the 70s. Most of these approaches use terms like systems theory, systems analysis, or systems engineering. These earlier flavors of systems thinking have left a bitter taste for many who consider them imperialist, positivist, managerial, controlling, reductionist, or instrumentalist. It's important to be aware that the much broader family of thought, known as systems thinking, extends far beyond these approaches, and that their shortcomings have been forcefully critiqued within systems thinking. In systems approaches based on a positivist or a structuralist epistemology, the systems idea often translates into a misleading belief that the systems approach is comprehensive. Now, that is only ever feasible in a narrow framing, and it can only be maintained in an approach that is analytic and decompositional, looking inwards. But critical systems thinkers maintain that a well-understood systems approach must begin with recognizing the tension between the desire to be comprehensive and the recognition that it is impossible to be comprehensive. So as Churchman put it, a systems approach begins when first you see through the world through the eyes of another. And shortly afterwards, in his words, the systems approach goes on to discovering that every worldview is terribly restricted. Now, critical systems thinking is not a program that can be completed to produce a systems theory. Instead, it opposes that purely analytic attitude that is prevalent even among systems thinkers, keen on breaking things into their components to understand them. And instead, it maintains that things can only be truly understood once they are seen as embedded into the environment. Context matters in systems thinking as it does in feminist thought. It's this critical approach to systems thinking that we're interested in. And there's also a historical reason to explore critical systems thinking. In the 1960s, in rationalistic systems approaches, such as operations research and organizational cybernetics, the scientific apparatus was brought to bear to shape societies for the first time, or at an unprecedented scale at least. Together with computing, these approaches had developed unprecedented mechanisms of large-scale prediction and control. Now, critical systems thinkers grappled already then with the implicit and explicit hybris of that project, but also with the epistemological and ethical challenges of legitimacy and the ethical implications of this. The critical turn they took and the insights they developed on the way remain invaluable today. Computing now is about to implement that project that the rationalistic systems approaches dreamt of in the 1960s, and it does so largely on the same epistemological foundations that underpinned rationalism then, despite well-articulated critiques in the meantime. Whether we consider this utopian or dystopian, there's a lot to learn from that history that can help us to orient systems design for sustainability and justice. For Churchman, a systems approach to real-world planning, today we would call it design, is motivated by what he calls the environmental fallacy. Essentially, that fallacy describes an approach to solving an identified problem without regard for the environment it arises in, and therefore without understanding the wider effects that the intervention or solution will have. The result, more often than not, is a situation that is actually worse than before. Increasing, for example, the energy efficiency of Bitcoin mining to solve the problem of Bitcoin energy consumption is one such example. The effect will be increased energy consumption, very likely. So instead of narrowing down the perspective, an actual systems approach has to begin by expanding it. But that very quickly runs into problems, because it's simply impossible to expand until everything has been considered. Furthermore, expanding the system of interest introduces additional actors and perspectives who may not agree with the framing. That's why for Churchman, a systems approach begins when first we see the world through the eyes of another. Now, in his book, The Systems Approach and Its Enemies, a very strange dialectic unfolds. The main protagonist, the planner, comes at the world with the best of intentions and an approach we would now describe as hard systems thinking. It's an approach to problem solving, applying the very best scientific principles and mathematical procedures, largely from operations research, to logically and analytically address social problems. Now, in that process, scientific propositions gain normative content in their application because they entail value judgments, real-life implications, and side effects. The planner, who in that book in the gendered language of the day is conceived as a man, is full of optimism and full of goodwill, but at every step of his planning he encounters difficulties, seemingly irrational objections brought forward by the enemies of the systems approach: politics, morality, religion, and aesthetics. Each objection seems to be unresolvable within the systems approach. In order to rationally refute the seemingly irrational objection of the enemies, the systems approach needs to sweep in additional parts of the environment. And in response to their repeated objections, the boundaries of the system under consideration continuously expand until the entire universe seems to be inside. It's a bit reminiscent of Borges' fable of the map that expands until it fills the territory, and then it's useless. Churchman didn't resolve this dilemma. Ulrich summarized his message very clearly. And when we read that, it makes sense to substitute design for planning. In the systems approach and its enemies, the systems approach, for the first time, has become truly self-reflective with respect to the normative content of its own quest for systems rationality. In Churchman's terms, the system approach cannot realize its search for the comprehensive rationality of planning so long as it seeks to absorb the enemies of such rationality, such as politics, morality, religion, and aesthetics. Rather, the systems approach can claim comprehensive rationality if it learns to reflect on its own limitations, namely by listening to its enemies and by understanding them dialectically as what they are, mirrors of its own failure to be comprehensive. So Churchman articulated that inability of analytic deductive rationality to handle other forms of reasoning, coupled with this uncomfortable realization that rationality itself is founded on commitments that cannot be explained by rationality itself. He did not go further than that, but his work expressed the conceptual foundations of the two major turns in systems thinking. The first in the 70s broke with positivist assumptions about the nature of systems as structurally present in the world and knowable. The core contribution was to acknowledge that traditional systemic approaches to problem solving cannot simply be transferred to the social world, because defining the problem to be addressed through a technological intervention is the problem. The presence of multiple legitimately diverse perspectives necessitates a way to find consensus on how to frame the problem. The resulting soft systems thinking, exemplified by Checkland's soft systems methodology, is interpretive. It uses systemic concepts to organize a discourse in a problem situation, but it makes no assumptions about how the real world is organized. That was an important step in applied systems thinking, but it was unable to recognize and address issues of power dynamics and inequality among the participating stakeholders. In response to that, the second major break in applied systems thinking resulted in the emergence of critical systems thinking. And the content of that will be the topic of our next session. Critical systems thinking, short CST, starts from the recognition that the systems idea of holistic understanding, understood critically, must begin with examining the inevitable selectivity of discursive claims about systems. This body of work emerged in the 70s initially and drew directly on a range of contemporary influences, including the work of representatives of the Frankfurt School, such as Habermas and Marcuse, and later the work of feminist scholars, as well as writers like Foucault. Together, this work represents a critical turn in systems thinking. The result is a heterogeneous set of approaches developed between the late 70s until now that aim to combine a critical approach with the intention to intervene productively in the world, to design and to create social change. They have in common a commitment to critical reflection, the emancipation of marginalized perspectives, and methodological pluralism. Now, Churchman already drew attention to a crucial dilemma. For a choice in systems design to be rational, it must of course contribute to the goals of the designer. Churchman called this figure the planner. But to decide what those should be requires an ever-expanding scope of systems design. To rationally evaluate even the smallest choice in systems design for situations in which elements are as strongly interconnected as in any truly problematic social situation, The designer must justify their evaluations by reference to larger choices, which in turn tie into broader concerns, and ultimately what the designer decides, explicitly or implicitly, amounts to a judgment over what is supposed to constitute the whole system of relevance. And these whole system judgments are necessary to make any real choice. Churchman articulated that struggle and the need for a dialectic approach, but he did not suggest a concrete framework for resolving that challenge. His advisee Werner Ulrich drew from contemporary critical social theory to continue this line of inquiry, and it's worth retracing some key steps of his somewhat difficult argument to interpret it from a contemporary perspective and resituate it in the context of systems design for the 21st century. Ulrich continues Churchman's questioning of the rational justification of the propositions of applied science with the simple observation that each whole system judgment, for example, whether a fact should be considered as part of the justification for a design decision or not, can be traced back to its underlying assumptions. When seen and questioned as a claim, it should be substantiated. The argument made for the validity of this claim in turn relies on assumptions that can be questioned, and so on. At some point, the justification inevitably breaks off, as visualized here. And the set of explicit and implicit claims at which justification breaks off is considered the reference system by Ulrich. Now, Ulrich is under no illusions about the homogeneity of those involved in making those judgments, those involved in design, or the willingness of those who are in power to open their justifications to scrutiny. His heuristic framework begins with the distinction between those involved and those affected in design. Either boundary judgments from before are built on implicit reference systems. From this distinction, Ulrich proceeds to develop a set of 12 heuristic categories that examine the different kinds of assumptions and conditions that give rise to boundary judgments. The boundary judgments where justification breaks off rely on judgments that are prior to the design effort. So the planner must trace the normative implications of alternative boundary judgments, alternative conceptualizations of the problem, and to make these implications transparent to those concerned, in Ulrich's view. So Ulrich looks for the crucial sources from which the normative content of any design derives and finds it in intentionality. Human intentionality is the constitutive element that accounts for the complex and normative nature of the object domain, social reality. Intentionality is what distinguishes the social world from the purely technical or the world of natural sciences. The purposes pursued by human actors and social groups introduce an entirely different kind of element into the object domain of design. And in introducing purpose, Ulrich directly opposes the main proponent of rationalistic systems design, Herbert Simon. Now, earlier, Akov had made a very useful distinction in the behavioral classification of systems into state-maintaining, goal-seeking, purposive, and purposeful. From a behavioral perspective, state-maintaining systems react to changes in the environment by adjusting their internal elements. They produce the same state under different conditions. A compass points towards the strongest magnetic field. A thermostat-based heating system regulates temperature. State-maintaining systems do not choose how they react. They're not capable of learning. In contrast, goal-seeking systems do not simply react to changes in the environment. They select different responses to external states to achieve a set goal. Autopilot systems are one example. Multi-goal seeking systems pursue different goals depending on their state. When the different goals of such a system have a common property, Akov calls it purposive. The system's purpose consists in producing that common property across different goals. Organs, such as the human heart, are an example. The heart will respond differently to external conditions, but its purpose is to regulate blood circulation. But it will set different goals depending on whether the body is under stress, resting, sleeping, and so on. Now, in contrast to that, a purposeful system can change its goals under constant conditions. It selects ends as well as means, and it thus displays will. Human beings, in Akov's words, are the most familiar example of such systems. Now, that distinction between purposive and purposeful becomes relevant once we consider organizations and socio-technical systems. For example, an individual person is a purposeful system, whose elements are purposive. The heart does not choose a different purpose. But in contrast, organizations are not only purposeful systems, but their elements too are purposeful systems. In Akov's words, an organization consists of elements that have and can exercise their own wills. Now, the critical difference between organisms and organizations can be made explicit. Whereas both are purposeful systems, organisms do not contain purposeful elements. The elements of an organism may be state-maintaining, goal-seeking, multi-goal seeking, or purposive, but not purposeful. What's interesting about this work is that, despite its very functionalist conceptual framework, Akov's distinction between purposive and purposeful systems becomes a deceptively simple mechanism for conclusions that have serious ethical consequences, because it becomes unethical to treat any purposeful system as if it was merely purposive, to treat it as if it was unable to select its own ends, because that means treating it merely as a means to the ends selected by someone else. Now, Ulrich's introduction of purpose into systems design does not rely on a behavioral classification, but on a principled argument. Just as causality is an important idea in the physical sciences, intentionality matters for understanding the facts of the social world, and it is in fact no less empirical in content than causality. Habermas's theory of knowledge-constitutive interests provides some departure points for evaluating claims made about system boundaries. There is no human knowledge without interest. Human interests are always a constitutive factor of knowledge. And there's a useful distinction to be made between technical interests in prediction on control in the domain Habermas labels work, practical interests of mutual understanding and communication in the domain that Habermas labels interaction, and emancipatory interests in autonomy and freedom. Habermas's concept of the ideal speech situation captures the idea of a situation in which participants can freely arrive at a consensus. That situation serves as a regulative idea. We cannot distinguish true consensus from false consensus unless we accept the idea of an ideal speech situation as a comparison point. But it is more than that, because in Habermas's view of rationality, the possibility of the ideal speech situation has to be at least presupposed in principle in any act of communication. For Habermas, any communication assumes 4 validity claims: that what is said is comprehensible, true, right, and sincere. Thus, we can ask a speaker, what do you mean? Is what you say true? Are you entitled to say that? And do you really mean it? As Outhwaite writes. So against this background of interest and purpose in a situation where claims are made about systems, the designers need to identify what the perceived social reality means in design. So they need to identify its location and significance in the spectrum of intentionality defined by the concerned actors, and those are the involved and the affected. So according to Ulrich, defining purpose as a mapping dimension analogous to space and time is not to introduce value judgments into social mapping, but rather to include in our basis of experience the value judgments that are always already there as constituent elements of both social reality and our maps of it. So Ulrich contrasts the rationalistic tradition personified by Herbert Simon's sciences of the artificial, which lives on very strongly in computational problem solving and rationalistic systems design, with the position established by Churchman. And some aspects of their opposing positions are especially worth a review. According to Ulrich, Simon excludes subjectivity from objectivity. Objectivity is the absence of subjective judgments, while Churchman includes it. Simon considers complexity as hierarchy. There's a famous paper about that. While Churchman would consider systems complex precisely when and because they cannot be described as hierarchies. Simon effectively denies the concept of emergent properties in holism. For him, the whole is not more than the sum of its parts, though the analysis is not trivial. Churchman definitely accepts the idea of emergence. Simon considers the ascription of purposes to social systems as a teleological fallacy, while in Churchman's view it serves a necessary critical purpose against hidden value assumptions. Maybe the most interesting comparison is the opposing view of what the crucial design task to be solved is. For Simon, it's problem decomposition. How to decompose a complex system into simple systems that are easy to be controlled, or how to design and control complex hierarchies. For Churchman, it's problem identification. How to describe unique systems, and especially how to identify the whole system on the one hand and the smallest system, the individual, on the other. While Simon privileges the divide and conquer standpoint that we see in computational thinking, and he sees a problem of control, Churchman privileges the ethical standpoint and sees a problem of boundaries. But as Ulrich adds, the most significant difference between the two positions might be that one, Simon, in principle denies their compatibility, whereas the other, Churchman, does not. So in other words, Churchman is not averse to relying on the powerful mechanisms developed by Simon's paradigm as long as their application can be ethically justified within a critical and reflective framework. Simon, on the other hand, demonstrates aversity to such an embedding. So in Ulrich's words, the problem of Simon's approach is clear. It simply avoids the moral and political question of how a better whole will result from incremental improvement of small and separate subsystems. It leaves that question to the market as a surrogate planner, and to the interest groups that control it as surrogate clients. The crucial task is not one of providing analytic tools such as social indicators, simulation models, etc., but rather dialectic tools to help the planner reflect and enter into reasonable discourse with the affected. No systems approach for handling real-world complexity can be rational unless it makes room for the self-critical reflection of free citizens, for these alone know what social reality is and what it ought to be like. The systems approach may yet have a great future if only it begins to understand that the enemies are really its allies. All Ulrich's words. So in other words, Simon's approach evacuates values and politics from the design discourse, and it has left behind a depoliticized science of design. The resulting analytic tools are powerful, but they're, in Marcuse's term, one-dimensional. Other systems approaches like cybernetics similarly do that and evacuate intentionality. Now, the project of critical systems thinking is not concerned with denying the validity or effectiveness of the analytic tools of hard systems approaches, but with undoing the evacuation of politics to support the integration of analytic tools into a critical approach in which their application can become legitimate and appropriate under clearly defined conditions. And it's difficult to overstate the importance of the difference in today's social reality of systems design, in which the legacy of Simon's approach still enjoys a hegemonic position. In contrast to Simon's approach, Ulrich proposes a critical interpretation of the systems concept. He says, if we take the systems idea seriously what it is, an unavoidable critical idea of reason, we must conclude that our designs are deceptive to the extent that we do not critically reflect on the whole system's judgments that inevitably flow into them. That is, our reflected or unreflected prejudgments about the relevant totality of conditions that we can never know as such. The fact that we never know the whole system does not imply we should keep the scope of inquiry within arbitrary boundaries and treat the environment as a given. And it's the designer's responsibility to secure the transparency of the boundary judgments and to trace their possible normative consequences. How do we do that? Ulrich's most significant contribution lies in a rigorously derived system of categories that allow us to develop meaningful questions about the reference system. And to develop these, he begins by asking, what are the whole system's judgments that are constitutive of the normative content of a systems map or design? And he lists 7 typical examples of boundary judgments. What is or should be considered as a problem, and whose problem is that? What purpose should the project serve, and who should belong to the group of those who are to benefit? What should be the totality of conditions that define the standard of success? What should be the time horizon with respect to the relevant conditions in the future? For instance, should the future generations be included within the problem-relevant client system? He even asks, is intergenerational transfer of costs or risk acceptable? Are irreversible consequences acceptable? And to what extent is the future to be part of the system, and to what extent part of the environment? Questions that resonate very much with sustainability, of course. And he also asks, what should be the time horizon with respect to the relevant conditions in the past? Should past generations, their goals and dreams, the traditions we inherited from them, belong to the problem-relevant system? Then 6, who might be affected by the project, by the change in the social system in question, although they do not belong to those who are involved and benefit? Under what conditions can we assume it's legitimate that some people are affected although they cannot belong to the client system? How do we draw the boundary between the affected and the unaffected in the case of long-term risks, such as sustainability? Who among the affected ought to be involved in the project? Oops. And finally, who does or should plan or design, and who ought to belong to the decision-making body? Who should belong to the experts and decision makers? Each of these questions represents a boundary judgment. I hardly need to elaborate the striking relevance of these judgments to sustainability and justice. For Ulrich, these boundary judgments are the departure points that motivate his development and justification of critical systems heuristics. In each situation, in any design effort, the set of implicit assumptions at which the justification breaks off constitute what he terms the reference system, the set of unspoken assumptions and conditions on which the justification for design is constructed. Now, the questioning of the explicit boundary judgments in their justification can to some degree make that reference system visible. And it's at that frontier that the selectivity inherent in all the worldviews becomes visible. Because power is the ability of an individual or a group to impose its purpose on others, Ulrich distinguishes between three classes of involvement according to their sources of power. The client represents sources of motivation, purposes, values, interests. The decision maker represents sources of control, resources, authority. And the planner represents sources of expertise, knowledge, skills. The group of those affected but not involved is more difficult to bound. Its members qualify not by virtue of influencing the design, but by virtue of being affected. Because of the vast array of potential effects and their dispersion in time and space, this group can become so large as to be of little heuristic use. Ulrich covers the whole array of dispersion later addressed so eloquently by Gardiner, including references to socio-ecological destruction, and he emphasizes that the group includes individuals to whom the planner cannot turn for hearing their concerns, be it because they're unborn, too young, or handicapped for other reasons. His question is how a design discourse can be rational even though not everyone affected can become involved. The key category is that of the witness. In his words, by virtue of their own affectedness, they can bear witness to the way in which all those who cannot voice their concerns may be affected. Their feelings, their suffering, their moral and political consciousness, their ways of expressing dissent, their ways of living the social reality in question, their vision of their own future. The planner cannot adequately trace the normative content of alternative boundary judgments without referring to some actors playing the role of a witness. So that category of the witness, in other words, translates into the crucial question of legitimacy. So the four categories are then crossed with three basic questions that ask for the social roles of the involved and the affected, role-specific concerns, and key problems in determining the necessary boundary judgments. This deceptively simple structure is unfolded into 12 heuristic categories in a dialectic process founded on democratic ideals. Sources of motivation unfold into the client, the purpose of planning or design, and the measure of improvement. There's never a perfect measure of improvement, but some measure is implied in every social design, and the existence of such a measure is a heuristic necessity. There's no design without it. In other words, the source of motivation constitute the value basis of design. Sources of control unfold into the decision maker, the components under the control of the decision maker, and the decision environment that provides the conditions outside of the decision maker's control. For Ulrich, the crux of the second category lies in tracing the sources of control that are or ought to be beyond the control of the system that is designed. That is, they ought to be in the environment. In other words, the sources of control constitute the basis of power. Third, sources of expertise unfold into the planner or designer, their expertise, and the guarantor of expertise. Deception arises crucially when it comes to expertise. Ulrich asks, how can the planner even know that the expert's skills, experience, or tools are not a source of deception, rather than a source of guarantee that improvement will result? The category compels the designer to examine the guarantors of expertise. And in Ulrich's words, no amount of expertise is ever sufficient for the expert to justify all the judgments on which his recommendations depend. When the discussion turns to the basic boundary judgments on which his exercise of expertise depends, the expert is no less a layman than are the affected citizens. In other words, this category captures the basis of knowledge. And finally, sources of legitimation unfold into the witness, their ability to emancipate themselves from the rationality of those involved, and the worldview underpinning the planning effort. The crux lies in the possibility of fundamentally conflicting worldviews, different visions and ideals of what life should be like. It is that fact, which we highlighted earlier as the crucial ingredient in the nature of wicked problems. In Ulrich's words, the essential point is that the affected must be given the chance of emancipating themselves from being treated merely as a means for the purposes of others. The figure here summarizes the conceptual relationship between the two types of boundary judgments, the categories of being involved and affected, and the resulting heuristic categories. The set of categories should be instantiated with attention to the context of design, so the exact terminology and focus varies accordingly. For each category, the key question can be asked in two modalities: an empirical "what is the case?" and an ideal "what ought to be the case?" Together, the categories in their two different forms can be used in at least three different ways: reflectively within a design effort, critically in a constructive engagement, and polemically by those affected but not involved in a case of undemocratic interventions to expose the lack of legitimacy of such undemocratic interventions. In other words, if we do this reflectively for ourselves, we can begin to understand how our own worldview is positioned in the world, how our knowledge is situated. If we do it as a critical friend, in dialogue with someone, we can help them understand the boundaries of their system of assumptions and how that is selective. And if we do it in a situation where someone involved but not affected is unwilling to engage, we can at least dialectically demonstrate to others what some of their assumptions are and that they are unable or unwilling to justify them. Critical systems heuristics, or CSH, has found a wide range of applications in planning and design, in the evaluation of sustainable development projects, or healthcare policies, and more recently also in understanding the politics of stakeholder involvement in systems design, and this will be of closer interest for us. But for now, I want to return to the question posed by Feinberg to connect the dots. Who is likely to first notice the limitations of the engineer's useful but narrow conceptions of reality? There is no meta-discipline able to predict the need to integrate multiple forms of disciplinary knowledge. Another source of knowledge must come into play. It appears that there is indeed someone ready to notice these limitations. There is a meta-discipline able to predict the need to integrate multiple forms of disciplinary knowledge. Critical systems thinking emerged to do almost precisely what Feinberg calls for. It provides a dialectical rationality that begins from the recognition of positionality and partiality that feminist STS also calls for. Ulrich's reference system and the way that others have further developed his ideas about boundary critique essentially conceptualize in systemic terms how knowledge claims are situated and how they are mobilized in design. The heuristics allow the demonstration that a given scientific or engineering method cannot justify its own assumptions, and that the legitimacy of so-called experts does not rest on their knowledge alone, but also on other sources of power. Only those affected can ultimately justify the normative implications of design. The heuristics use logical ways of reasoning that are actually quite accessible to those with a computational background, but the underlying social theory is challenging. It appears to me that one reason why these strands, critical systems thinking and STS at Feinberg, have not met earlier, aside from the detrimental effects of disciplinary isolation that systems thinkers precisely pointed out, is to be found in that strong pushback against instrumentalist systems theory. Well, over the past 20 years, feminist STS has been vibrant and active and more in tune with technological developments than CST. It has moved beyond CST in several ways through its substantive material and empirical attention to concrete categories such as gender, race, class, and ability, through the conceptual framework of intersectionality, and through many other lessons of decades of feminist technoscience research. But as Ulrich writes, the anti-holistic argument mistakenly assumes that the systems idea causes the difficulty of which it reminds us, the inevitable lack of comprehensiveness in our maps and designs. I would agree with the critical systems thinkers that a perspective that is critical but not systemic will be ineffective or mistaken, because the boundaries of the argument either remain implicit, which severely limits the degree to which the inquiry can be critical, or they become subject to continual expansion. On the other hand, perspectives that are systemic but not critical will be harmful and unethical. The critical idea and the systems idea need each other. The critical turn in systems thinking is an illustration of the extrication from instrumental thinking into a critical technical practice that Phil Agre also struggled with in the 90s. Today, feminist data scientists and their allies also find themselves in a similar dilemma to the critical systems thinkers. They don't want to abandon technology or data science. And of course, data must be categorized to be data. So they need to find a way to work with categorization while constantly challenging it. Just like the critical systems thinkers needed to find a way to think systemically while grappling with the inevitable selectivity of their claims. Just as data feminism is not ready to abandon the nutritious grounds of data science with all the powerful tools that are there, CST decided not to abandon the powerful tools of systems thinking, but put them to ethical use. The resolution of the tension between critical and constructive generative perspectives is enabled by systemic thought. It's critical systems thinking that allows a critical approach to become generative and a generative approach to become critical. But that's not to say that critical systems thinking has all the answers. It placed the emphasis on partial perspective, selectivity, and emancipation at the center even before feminist SDS did. But intersectional feminism today is much more nuanced in its attention to concrete categories of power, such as gender, locality, race, ability, experience, and so on. CST focused in more nuanced ways on abstract systems ideas, boundary judgments, and legitimate justification, and that is what we can learn from it in a variety of contexts. So to recap in simplified terms, CST aims for critical reflection on normative claims, emancipation, and methodological pluralism. In Ulrich's words, under the guise of rationality and expertise, the involved often make themselves the client while treating the affected as a means. It's only by giving an equal status to the rationalities of the involved and the affected that we can prevent the former from making themselves the judges who define the measure of improvement. In short, the affected must be helped to emancipate themselves from the rationality of the involved, from the promises and premises of the experts. So we need a dialectic of expertise and emancipation, of professional competence and democratic participation of citizens. The critical systems heuristics are not meant as a checklist that gets filled out and put aside, but as a starting point for discourse and a continued central issue of investigation and reflection. As he writes, a well-understood systems approach begins and ends with the questions we ask, not with the answers we give. And with this quote, I will close this brief reunion of computing's critical friends. Thank you for watching.